Good morning and welcome to the final lesson of grade 8 math for this school year. I know I'm not your typical teacher, so I want to give a quick introduction. My name is David Dye. I am currently in my third year of teaching at Alma Bryant, or third year of teaching and second year at Alma Bryant High School. And this semester I am teaching algebraic connections and discrete math. So for this week, I want to spend our lesson kind of focusing on what you might see in Algebra 1 next year. And really focusing on this idea of functions and then how we can focus our attention towards creating algebraic models with this idea of functions. And so my learning goal today for you is that we're going to introduce you to functional relationships and then for you to be able to look for patterns and develop algebraic models of those functional relationships. So really taking the stuff that you've done the last couple of weeks from a geometric perspective with volume and surface area and the scatter plots that you kind of looked at last week, we're going to transition and look at functional relationships. So the agenda for today, I'm going to introduce you to functions, kind of establish a definition for what that is, and then we're going to take a look at a task called the painted cube. And then we're going to use that to establish really more formally how we can make sense of functions. And then we're going to talk about your chance to win a prize towards the end of the lesson. So when we're talking about this introduction to functions, I want you to consider what is going to happen next in each of the following situations. So the first situation I want to bring up is this idea of typing in a code for a snack machine. So you put your money in, you type in A4. I want you to think about what's going to happen next. And then dialing 911. So if I pick up a phone, I dial 911, I hit call. What do you think is going to happen next? And then lastly, you make all A's next year as a freshman. What's going to happen next? And so when we're looking at this snack machine idea, if I type in that code A4, a specific snack is going to come out. If I put that money in and I'm typing in this code and I want M&Ms, I type in the code for M&Ms and that's what I'm going to get. But if I wanted Twix, I'm going to type in another code and that's what I'm going to get. So unless the machine is wrong or broken, you're going to type in one code and you're going to expect a certain outcome and you're not going to get something else. Or on the other hand, you're not going to type in A4 and get both M&Ms and Twix. So a specific input is going to give you a very specific output. Same thing with dialing 911. You're going to get a law enforcement dispatch answer. You're not going to type 911, hit call, and grandma's going to pick up. Or your uncle's going to pick up, unless, they work for the law enforcement. But, with that specific phone number, you're going to get a very specific person on the other end of that line. And then making all A's your freshman year, you're going to earn a 4.0 GPA. At the high school and the collegiate level, each grade has a corresponding point value. An A is worth 4 points, a B is worth 3. So if you're making all A's, then you're going to have a 4.0 GPA. You're not going to have a 3.0 GPA. And so all of these situations, I want you thinking about how we're given a specific input and we expect a certain thing to come out. We expect something specific to return based on the input that we're given. And so that's really how we describe functions, is that when we have a unique input, a unique output is given as a result of that input. Okay, I put one thing in, I expect something else to come out. And we're going to use this particular definition and the painted cube task to really explore that idea. So with this task, I want you to take a look at the image that I'm showing you here. In case 1, we see that we have this 1 unit block. And then in case 4, I want you to notice that we're looking at this cube that is 4 across, 4 in height, and then 4 in its depth. So this cube dimension is going to be a 4 by 4 by 4. And so the question that I'm going to pose in a second requires us to understand the context that if we have this particular cube, a 4 by 4 by 4 cube, and we painted all of the faces, so this entire thing is covered in paint, I want to know how many of these smaller cubes, these unit cubes, how many of those are going to have 3 of its faces painted? How many are going to have 2 faces painted? How many will have 1 face painted? And then how many are going to have no paint on them at all? So how can we begin to answer these questions by looking at this particular model? And then once we answer those questions, I want us thinking about what happens if I have any size cube. How can I answer these questions? And again, all of this with the lens of functions. Does it matter the case number that we're looking at to determine the answer to these questions? So when we're looking at this 4x4x4 cube, all of it's covered in paint. What I'm going to show you here is kind of the location of where each of the unit cubes, the ones that have 3 faces painted, 2 faces painted, 1 face painted, and 0 faces painted, I'm going to show you where they're located. And I want you to think about how many of each type there are. So in this particular image, I'm showing you where the location of the 3 faces painted are going to be. Again, paying attention to the location. Here is where the 2 faces of our unit cubes are painted. Here is the location of the 1 face painted. And then when I take away all of the unit cubes that have paint on them, what's revealed is this smaller cube on the very inside when I remove all of the other cubes that have paint on them. So how many have 3 faces painted? How many have 2 faces painted? How many have 1 face painted? And then how many don't have any paint at all? And I really want you thinking about location and thinking about whether or not any of these are shared. So as we think about this, the 8 cubes that have the 3 faces painted on them are all located in the corner of our larger cube. So all of these are corner pieces. And then when we're thinking about the cubes that have just 2 faces painted, if I take away the corners that we started with, these cubes are all along the edge of the larger cube that we're looking at. And then when I remove, or let me backtrack. If I'm looking at these edges, I've got 24 total cubes that have 2 faces painted. And so I want you to think about where all of these edge pieces are and how many edges there are on this larger cube. For the 1 face painted, if I remove the corners and I remove the edge pieces, we're left with the smaller square in the face of our larger cube. And there are 24 of those. And then when I take away all of the cubes that have paint on them, we're looking at a situation where I've got these 8 cubes in the form of a smaller cube in the very inner part of our larger cube. So my question as you are continuing to think through this is, does the number of these cubes that have 3 faces painted, 2 faces painted, 1 face painted, and none painted, is that related at all to the case number? Right? Is this a functional relationship? Is kind of the question that we want to explore. And now that we have these counts, the idea for us to explore next is, what happens if I change the size to any size? Can I make that kind of prediction for how many of these cubes are going to have these certain number of faces painted? And the way we're going to address that is we're going to kind of backtrack and look at smaller cases. If you recall the first slide I showed you with the painted cube, we had case 1 and case 4 shown, with case 2 and case 3 as question marks. Let's explore those real quick. So with case 2, I'm looking at a 2 by 2 by 2 cube. And if I dump that whole thing in paint, all of the cubes are going to have exactly 3 of their faces painted. And then if I'm looking at a 3 by 3 cube, and I cover that entire thing in paint, what we have here is that there are 8 cubes with 3 faces painted. And again, pay attention to the location. Right? These are also in the corners of our larger cube. If I'm looking for where the 2 faces painted are, I have 12 of them on a 3 by 3 by 3 cube. And again, look at the location, and these are along the edges of our larger cube. If I remove the corners and the edges, that leaves us with the square in the middle of our faces, and that's going to give us 6 cubes with exactly 1 face painted. And then if I take away all of the cubes that have paint on them, we're left with this inner cube, and there's only 1 of those. And so as we're looking to define a function, and remember, I'm telling you that a function gives us a unique output given a unique input. So the unique output that we're interested in is the number of cubes with the certain amount of faces painted. And then the input that we're considering is our case number, a 2 by 2 by 2 case, a 3 by 3 by 3 case, a 4 by 4 by 4 case. So in order for us to really explore whether or not there's any kind of functional relationship, I think it's productive for us to organize that information into a table. So if I looked at case 1, here we're only looking at a single cube. And if I cover that entire cube in paint, then there's no way for it to have just 3 faces painted, just 2 faces painted, 1 or none. So I'm going to fill this in with zeros. The 2 by 2 by 2 case that we looked at previously on that last slide has a total of 8 cubes. And if I painted the entire thing, we stated a second ago that all 8 of them are going to have exactly 3 faces painted, which means this is going to fill out to be 0. And again, I'm creating this table structure for us to determine whether or not there is any kind of functional relationship. Can I have a unique output based on this unique input? If I'm looking at the 3 by 3 by 3 case, we have 27 total cubes, 8 of which will have 3 faces painted. And again, thinking about the location where those are, we have 12 that have 2 faces painted, 6 with 1 face painted, and then 0, that inner cube with no faces painted at all. There's 1 of those. In the 4 by 4 by 4 case that we looked at originally, we have 64 total cubes. Again, there are 8 that have 3 faces painted, and then 24, 24, and 8 to fill out the rest of that table. So before we look at the 5 by 5 by 5 case, again, looking at this idea of functions and how a unique input is going to give us a unique output, can we make any kind of predictions for what these values are going to be based on the patterns that we might be seeing here? And the thing that I want to bring up first is this total number of cubes. How do we get 1, 8, 27, and 64 if I just know the dimensions? Well, what happens when you multiply these numbers going across? So 1 times 1 times 1 is going to give us 1. 2 times 2 times 2. So 2 times 2 is 4, times 2 again is 8. 3 to the 3rd power gives you 27. 4 to the 3rd power gives us 64. So the total number of cubes in case 5 is going to be 5 cubed, which is 125. And now if I'm looking at the situation where I have 3 faces painted, think about what these values are and think about whether or not they're changing. I'm looking at 8 here for my corners, 8 for the corners here. In the 5 by 5 by 5 case, the number of corners does not change. So the number of cubes that have 3 faces painted doesn't change. And I want you thinking about whether or not that fits our definition of a function. A unique input should give me a unique output. And we'll come back to that idea in just a second. Here with the 2 faces painted, on my 5 by 5 by 5, I want you paying attention to the location. These were along the edges. So in a 5 by 5 by 5 case, if I'm going 5 across and I take away those corner pieces, now I'm left with 3 along each edge, and I have 12 edges on a cube, so 12 times 36 is going to give me that value. When I'm looking for 1 face painted, if I'm thinking about location again, that was the very center of our faces on our larger cube. So when I take away those edges, that leaves me with a 3 by 3 center cube, or center square. And then 3 by 3 is 9. I've got 6 faces, so I have a total of 54 unit cubes that have 1 face painted. And then when I remove all of the layers of cubes that have paint on them, what we're left with is a 3 by 3 by 3 cube in the very center that has a 27 total of 0 faces painted. So what happens if I have any size cube? How can we take the information that we have here and think about any size? Well, if I'm looking at the dimensions in order to identify the total number of cubes we're dealing with, notice that this 8 is equal to 2 cubed, 27 is 3 cubed, 64 is 4 cubed, 125 is 5 cubed. So for any size larger than this, it's simply going to be whatever my dimension is to the 3rd power. It could be 100 to the 3rd power, it could be 20 to the 3rd power, and that's going to give me the total number of cubes that we're interested in. For the 3 faces painted, again, I want you thinking about the shape of our cube. If the corners are where the 3 faces painted is located, then no matter the size of my cube, whether it's 100 by 100 by 100 or 20 by 20 by 20, I'm still looking at just the corners. And so I'm only dealing with 8 cubes that will have 3 faces painted. When we're looking at the 2 faces painted, again, paying attention to location, right? The 12 for the 3 by 3 by 3, the 24 on the 4 by 4 by 4, these were along the edges of my larger cube. And when I'm looking at a cube, we've got 12 edges, and that expression that we can come up with is 12 times n minus 2. That 2 being the 2 corners that I take away on each edge. Here, when I'm looking at one face painted, so I'm taking away the corners, I'm taking away the edges. The other feature of our cube that we're interested in is the face of the cube itself, that inner square in the middle of each face. And so here, because a cube has 6 faces, the expression that we can model with is 6 times n minus 2 squared. And then lastly, when I'm looking at 0 faces painted, here when I remove all of the cubes that have paint on them, and I'm looking at the very inner part of that cube, we're looking at a situation where that inner cube is modeled by this expression n minus 2 to the 3rd power. And so this idea of functions, we can take what we have here in these expressions and we can graph them. So each of these features, the corners, the edges, the faces, the inner cube itself, we've got these different expressions that we can rewrite as equations, and we can then graph them in order to establish whether or not there's any kind of functional relationship. So here, the corners, as we stated, is always going to be 8, so that's something that's going to be constant. But I want you again thinking about that definition for a function. If I gave you a unique input, 5, I've got 8 corners that are going to have 3 faces painted. If I gave you 14, you're still going to have 8 corners that have 3 faces painted. So are those unique outputs for these unique inputs? Here in green, we see this line, so this linear function, for 12 times the quantity n minus 2. And that's going to give us our graph there. And I want you thinking about, if I gave you a unique input, like 5 and 10, are those going to be the same answers? Am I getting the same output? In blue, we're going to have our face cubes modeled. We call this 6 times n minus 2 squared function a quadratic function. And look at how that's behaving here. And then lastly, in purple, we're graphing our inner cubes function, the n minus 2 cubed. And that's what we see in purple. But again, with each of these examples and each of these graphs, if I gave you a specific number, you're going to get one answer. If I gave you 5, you're going to get a specific answer for that particular cube. But then if I gave you another cube size, 6 for example, are you going to get the same result? And if not, then we can't really say that this is a function. So, with that being said, earlier I mentioned this idea of you being eligible to win a prize. So I want you to really pay attention to the expressions that I'm giving you on this particular slide, with our corners being modeled, our edge cubes being modeled, our face cubes, and then the inner cubes. And these expressions are going to be your key to answering the question that I'm going to pose for your opportunity to win. So what MCPSS is doing is allowing the students who are viewing these lessons to submit answers to questions that the teachers are posing. And with a correct answer submission, you are eligible to win a Chick-fil-A prize or a t-shirt from MCPSS. So here's your chance to win. And again, I want you thinking about the questions that I've posed throughout the lesson, the idea of functions, the idea of the number of faces painted for each of these. And so here's the problem. If we were to paint all of the faces on a 10 by 10 by 10 cube, I want you to think about how many of those smaller unit cubes would have 3 faces painted, how many would have 2 faces painted, how many would have one face painted, and then how many would have 0 faces painted. So here is our case number 10. And just going back a couple slides really quickly, how can I use the number 10 in the expressions, or rather the equations that I'm modeling with, to make the predictions that I need in order for you to have a chance at winning? So if you haven't had the chance to do so, I would make sure you write down these equations somewhere handy. And then once you're done writing, I'm going to go back to that final problem in about 5 seconds or so. And so again, we're considering the 10 by 10 by 10 cube situation. And once you have your answer, you can email your answers to mcpsstv@mcpss.com. They'll assess whether or not your answers are correct. And then with a correct submission, you have the opportunity to win. And I think they'll contact you once those details have been finalized. It's been my pleasure teaching you this final lesson. I hope you all have a great summer.